Okay, so let's take a look at a two-step mole problem. What we mean by a two-step is the following. You'll notice that in this problem, what volume is occupied by a 53.25 gram sample of Cl2 gas? You'll notice that we're beginning with grams. We want to know what volume does that occupy. So what's happening is we're given 53.25 grams. Now we cannot go directly to volume. Instead, we're going to convert grams into moles and then convert moles into liters. Now that makes this a two-step problem. This is step one, converting grams to moles, and then step two, we're going to have to convert the moles to the liters. Now there's another added piece to this. You'll notice that in this example, grams are involved. As soon as you see grams in a problem, you must now solve for the molar mass of the molecules, because that's going to come up. So what we do is going to come over here, we're going to write Cl2, and we want to know the weight of Cl2. This is a format we've been working with for a while, and so I'd like you to always follow it. Chlorine weighs 35.4. There are two of them. And so the total weight of this molecule is 70.8 grams per mole. Again, that means if you have 1 mole worth, which is 6.02 times 10 to the 23rd Cl2 molecules, if you have that many, it's going to weigh this much. Now, what we want to do is we now got to go back to the weight. We got to go to moles, and from moles go to liters. So how are we going to do this? Well, we're going to use dimensional analysis. You're required to. And when you do dimensional analysis, you write down the number you are given, which is 53.25 grams. Put it over 1. Now what you do is, since you have grams up here, you got to get grams down here. And here you're going to use one of your unit ratios. So what we're doing is going from grams to a mole. That's our first step. That's what this right here is doing. So we know that 70.8 grams is a mole. So we're going to write down 70.8 grams is 1 mole. Our grams cancel, and cool. We've now moved into moles. We can't stop there. We want to go now into liters. So, if you have moles up here, 1 mole goes down here. And what we're going to do is, when it comes to gases, 22.4 liters will hold 1 mole worth of a gas. You'll notice our moles cancel. Now when you multiply the numerators divided by the denominators, you come up with 16.85 liters of Cl2. There's your answer. Now the question is this answer reasonable? Let's see. We had 53.25 grams. 70.8 grams is 1 mole. This is less than that amount. So I should have less than 1 mole. But wait a minute. 1 mole occupies 22.4. But I have less than a mole, so I should have less than 22.4 liters, and I do. So that answer is reasonable. Right, let's take on a new problem. In this case, how many grams are in 353 3.55 times 10 to the 18th molecule sample of NH4H2PO4. Okay, how are we going to break this down? Well, the first thing we want to recognize is, I need my proper pen here. First we want to recognize is we're seeking grams. Now see, as we get grams going, I know I need to solve for a molar mass. In addition, I want to find out how many grams from this many items. So what it is I have a certain number of items, which is 3.55 times 10 to the 18th. I can convert the number of items to moles. Once I know how many moles I've got, I can go for grams. So this, once again, this is a two-step problem. Now again, because I see that we're working with grams at some point, I need to solve for the molar mass of this. So let's do that right now. So the material is NH4 H2 PO4. We want to know the mass of that. Well, nitrogen weighs 14.01. There's one of them. Hydrogen weighs 1.01. But there are two here, four here, two there. There are 6 of them. Phosphate weighs 30.9. There's one of them. And oxygen weighs 16, but there are 4 of them. If you multiply and sum that up, you wind up with 115.04 grams for every mole. Remember, it's a mole worth of this molecule, so I count out 6.02 times 10 to the 23rd of these molecules. Okay, now we gotta solve this. So in dimensional analysis, we always start with the number given to us. So it's 3.55 times 10 to the 18th. That's the number of items. You put that over 1. Now what we do is we go through our conversions. So here's our first unit conversion. If I have number of items up here, I get number of items down there, and the conversion is 6.02 times 10 to the 23rd is 1 mole worth of material. So we just went from our numbers, we've converted to moles, but we're not there yet. We now got to move on to grams. So, it's going to be a tough fit. So, 1 mole of this weighs 115.04 grams. So notice, this is a unit ratio of moles and grams. This is a unit ratio of number of items to moles. And that's, of course, what we start with. Now, because I want to make sure we're clear on the math here, I'm going to carry this down. And what I'm going to do is I'm going to multiply all of my numerators. First, I'm going to cancel. So numbers cancel with numbers. Moles cancels with moles. So what we do is we got 3.55 times 10 to the 18th multiply that by 115.04 grams. Okay? Now what happens is we put that whole amount over the denominator, which is 6.02 times 10 to the 23rd. Now what we're going to do here is we're going to take, to make this work, we're going to multiply the 115.04, we're going to multiply that times 3.55. So that's going to equal 408.25. Yeah, but what are you going to do with this exponent here, the power 10 to the 18th? And the answer, you just tack it on. So we have that times that, and that's going to be times 10 to the 18th. And that whole thing is going to be divided by 6.02 times 10 to the 23rd. Okay? Now we've done this before. You take these two numbers and divide them, and you're going to take these exponents and subtract them. And when you do that, you're going to get 67.81 times 10 to the minus 5th grams. And that then is your number. And as always, we should check this. So take a look up here. 3.55 times 10 to the 18th. 1 mole is 6.02 times 10 to the 23rd. Wow, this is a very small number compared to 10 to the 23rd. So we should have a lot less than 1 mole. Well, 1 mole weighs 115. The amount this should be way less than that, because we have way less than 1 mole of items. Sure enough, this is times 10 to the minus 5th, so it seems reasonable. Okay, so for the last problem, let's take a look at this. How many liters are occupied by 4.35 times 10 to the 20th molecules in a sample of O2? Okay, so what we're going to do again is we're going to go from a number of items, take it to a mole, and once I have the number of moles, I'm going to take it to liters. And that is a two-step problem. Now, again, we look here and say, is there any grams being asked for or worked with? No. So what you do not want to do is you do not want to do this. You don't need to, because there's no grams being asked for or worked with. So we punch it straight in. So we start with the number given. So you're going to get 4.35 times 10 to the 20th. That's the number of items. You put that over 1. Then you do the next unit ratio. And the unit ratio here is going to be, if I have number of items here, I get number of items down here. And you get 6.02 times 10 to the 23rd. And that's going to be 1 mole's worth. So these two went from numbers to moles. Now we got to convert moles to liters. So now what we do is we set up another parentheses. Moles is on top, moles is down here. And now we're going to go to liters. So 1 mole is 22.4 liters. So that numbers cancels numbers, moles cancels moles, and now we're at liters here. If we now crunch out the numbers, the video is going a bit long, so I'll go straight to it. If you punch out the numbers, you're going to get 16.19 times 10 to the minus third liters. Does this make sense? Well, 4.35 times 10 to the 20th, 6.02 times 10 to the 23rd is 1 mole. This is less than that many. So I'm going to have less than a mole worth of material. 22.4 liters is 1 mole. I should have a lot less than 22.4 liters. Sure enough, I do. So the answer makes sense.